Hello, I welcome you all to this another interesting screencast where we're going to be solving this engineering mechanics statics problem, and it reads determine the normal force, shear force, and moment at point C. I'll also include and draw the shear force diagram and the bending moment diagram. Okay. This problem is coming from the engineering mechanics statics textbook, 13th edition by R.C. Hibbeler. Okay, so we have a simply supported beam with two concentrated loads, and we have been asked to find the normal force, shear force, and the moment at C. But I've also included additional stuff that is not part of the problem. Okay, this I just included it. Right. So to start with, quickly let's draw the free body diagram. So at the hinge, we expect two reaction forces, AY and AX, and BY. So let's apply the equations of equilibrium. So we'll have summation of moments about point A, and clockwise being our reference. What we have? We have a negative moment 10 times the lever arm 1.5. Okay, so we want to find support reactions. Then we have a 15 times 4.5, right? And then we have by times 6, right? Equal to 0. Therefore, by is going to be equal to, so we have minus 10 times 1.5 minus 15 by 4.5, and then divided by 6. So this gives us a 13.75. Okay, so this gives us a 13.75. So let's find the value of AY. So say summation of forces in the Y equal to 0. What we have AY plus BY minus 10 minus 15 equal to 0. And since we found our by already, we'll just replace it there. And when we do so, we'll find that our ay is equal to as 13.75 minus 10 minus 15. So ay is equal to 11.25. So let's replace this here. This is 11.25, and this is 13.75. Right. And then we have summation of forces in the y, summation of forces in the x direction equal to 0. Okay. And of course we know that ax is just going to be equal to 0. Right. So let's make a section of the beam at C. I'll use the left hand side. We have the left hand side, and we have the right hand side. Okay, so I'll use the left hand side. Doesn't matter which one you use. So let's get that section. Let me draw the beam like so. So let's say this point is my A. I have my reaction force there, which is 11.25, and then I have my force here, and this is 10 kilonewtons, and then I have this distance there, this distance up to there where I've done the sectioning, and this is a 1.5, and this is a 1.5. These are both meters. This is kilonewtons, and so is this one here. Okay, let me just remove those units there. Okay, this point is C. So at C, we expect the internal forces shear in this direction, which is our VC, and then we have our moment, which we are calling MC, then we have our normal force. Okay, this is our positive convention. Okay, when we do a section and then we are using the left hand side of the section. Of course, the other side also will have same magnitudes but just opposite direction. Okay, all right, so here we go. Then the length from there to there is 3, of course. So summation of forces, let me start with moments. Summation of moments about point C equal to 0 and clockwise being my reference. What do we have? What do we have? Right, there we have the support AY is going to give us a negative moment, so it's 11.25 times 3. Okay, and then we have a 10 which is giving us a positive, which is a 10 by 1.5, and then that's it, and then plus the actual moment that we are looking for equal to 0, and therefore our MC is just going to be equal to, let's calculate, it's minus 11.25 times 3 plus 10 times 1.5. Okay, let's calculate. So we have 11.25 times 3 plus 10 by 1.5. Alright, so MC is equal to 18.75, right? Great. So let's go to the other side. Okay, then let's find the shear. So say summation of forces in the Y, equal to 0, like so. Then we have 11.25 as positive minus 10 minus VC equal to 0. and therefore our VC is just going to be equal to 11.25 minus 10. Our VC is equal to 1.25. Okay, so this is kilonewtons, and this is kilonewtons meter. This is kilonewtons, and this is kilonewtons in that manner. And then we have finally summation of forces in the x direction equal to 0. Okay, and then what we have is just NC is equal to 0 kilonewtons. Right, so we have found the support reactions, but the most important was to find the normal force, shear force, and the moment at C. So we have the moment, which I'm outlining right now in red. MC equal to 18.75, VC equal to 1.25, and normal force NC equal to 0. But we'll go further to just draw the shear and the bending moment diagram. So the way we are going to draw this, we are just going to use just the differential equations that relates the load, the distributed load, to the shear force, and later on to the moment. So I know that you must have come across. Of course, we're going to use equations later on in the other questions that are going to follow. This is just one of the techniques. I know it's a technique that is ahead. Yeah, okay. So we know that the rate of change of moment with respect to x is equal to shear force, and the rate of change of shear with respect to x is equal to the distributed load Q. And if this is the case, therefore we know that shear itself, okay, is equal to the area under the loading diagram. Okay, and we also know that moment therefore is equal to the area under the shear diagram. So with these two differential equations, we are going to make a drawing very quickly with the boundary results that we already have at A and B. Okay, so with these boundaries, it's possible for us to move and draw our shear force diagram and bending moment diagram very fast. All right, let's do that. This is just an additional, it was not part of the problem. All right, there we go, something like that. Okay, let's bring this a little bit down like so. All right, so let's call this one here as the shear force diagram. And then this one as the bending moment diagram. Okay, so let me create a boundary here. I create a boundary, something like that. And then we have on top as our positive, and here negative, and positive, and here negative. Right. All right. I move this a little bit. Oh no. Okay. Right. Let's start. I'll be using green as I draw. So at A, which is our initial boundary, and the boundary values that we have at A, we have AY, which is the reaction force in the vertical direction. So this is what we are going to start with. So we are going to move upwards by that magnitude of 11. Okay, let's say we are going up to there. All right. So once we reach that point, which we are going to call as our 11, let's write it down. That is the value. This is 11.25. Okay. So when we reach there, when we check between 11.25 and 10 kilonewtons, there is nothing. All right, there is nothing. So when we come here, we don't have anything there. Therefore, it means where can I write? Our Q in that region is equal to 0. All right, we don't have any loading in between 11.25 and 10 kilonewtons. Our Q is equal to 0. And if our Q is equal to 0, therefore our dV over dx is going to be equal to what? 0. Okay. The slope will be 0 in that region. All right. So to the point where we have 10, and that's the reason why we normally draw this straight line which has a 0 slope. Like so. We reach there. The moment we reach there, we have a point load. Okay. This point load will need to interact with this 11.25. They'll either add or subtract depending on the sign. So when you look at 11.25, it is positive, all right? And then 10 is negative. So they'll add up algebraically, all right? So 11.25 minus 10 kilonewtons. What do you have? You have a 1.5. So you expect this to reduce up to 1. Let's say 1 is somewhere there. All right. So this point here becomes our 1. This one becomes our 1.25. So it becomes our 1.25. Okay. So again, the same principle from 10 to 15 in between this region. We don't have any loading. Therefore, the slope of the shear force diagram, or just the slope of the shear, is going to be equal to 0. Okay, so we just expect a straight line again, a straight line up to where we have 15. The moment we reach that point where we have 15, what happens? They'll interact again. Okay, so 1.25 is positive while 15 is going down because we are using this convention. So we are saying, what are we saying? We are saying positive up, like so. Okay, so since 15 is negative, 1.25 is a positive, so we are saying it's going to be 1.25 minus 15. And what does it give us? It gives us a 13, a minus 13. So this will have to go down like so, maybe up to somewhere there. Let's say that is our 13. Okay, let's say up to there. Let's say that is our 13. So let's say this is our 13.75 kilonewtons. Okay, So let's say this is our 13.5 kilonewtons up to there. Alright, again between 15 and 13.75, we don't have anything there for the slope. It's going to be 0. Okay, so again it will be 0 up to that far end, and then later on again we have this other force, which is the reaction force, and they will have to interact again. So we have a minus 13.75 and a plus 13.75. So what happens? They will interact again algebraically. And what does it mean? It means our shear is going to move and close at that point. Alright, so we have positive shear, then we have negative shear. Okay, so we are done with the shear diagram. What we need to draw now is the moment diagram. So let me move this a little bit down like this up to there. Maybe I move it up to there like that. Okay, let me put a minus somewhere there. So again here, the same principles are going to apply. Alright, there we go. So there we go. We know that the area under the shear diagram gives us the moment. You've seen this? The area under the shear diagram gives us the what? The moment. Okay. So what we just need to do is to find the area. Okay. And then we'll look at the nature of the shear force, then relate it to the slope of the moment. So let's first do the first thing, which is finding area. So from 0 to 1.5, we can find area, right? Just L times B, so it's 11.25 times 1.5. That gives us a 16.85. Okay, so now we have 11.25 times 1.5, which just gives us 16.875. Okay, so this is the value. So when we look at the shear is constant. Okay, it's positive and it is constant. Positive, constant. Okay, so now because our shear is constant, positive and constant, you expect the slope. Look at this here. Look at this equation. So the slope of the moment will also be positive and constant. All right, to be positive and constant. Okay, so we have shear equal to 11.25, which is constant, and therefore our slope dm dx will also be equal to 11.25 as in the slope. And then we need to consider the boundaries at A. We know this is a hinge, so you don't expect a hinge does not resist any moment. Alright, and we don't have any applied couple moment at A. Therefore, we expect the moment to start from the moment to be 0 at A, and it will have a positive constant slope. Okay, so it is going to move from there. It will move from A going up to where we have, let's say where we have that point where we have a 10. Okay, I don't want it to be so high because I don't have space. Let's say it's up to there. Then this value here is 16.875 kilonewton meters. Okay, I'll write it later on. Let me write it 16.875 0.875 kilonewton meters. All right, so this is the point here. Of course, and then we from 10, okay, or from 1.5 to 4.5, the shear is again constant. So you expect again the slope of the moment to be constant, and the shear is positive, so it's going to be the slope is going to have a constant positive slope. Okay, the slope of the moment is going to have a positive constant slope. So what is this magnitude? This magnitude is 1.25 times 3, which is equal to 1.25 times 3. This is equal to 3.75. But mind you, at 1.5 we have a 16.85, so it will have to interact with 3.75. Okay, so since both of them are positive, when they interact they'll just add. All right, so it's 16.8875 plus 3.75. 16.875 plus 3.75. So this gives us a 20.65. So it will move up again. Let's say up to somewhere there like that. It will move up to there like that. Okay. So that point there we said is a 20 point. Let me write it. Is a 20. This is a 20.625 kilonewton meters. And then finally, we have from 4.5 to 6, we have a negative slope, but it is also constant. So what this means is the slope of the moment will be constant but with a negative slope. And this magnitude, just need to calculate it. This magnitude is 1.5 times 13.75, which is equal to, so 1.5 times 13.75, so it gives us a 20.625. okay, and since this is negative, it will interact with this, and when minus 20.65, 20.625 plus 20.625, one is minus, the other one is positive. When they interact, what do you expect? You expect this to be 0, right? To hit somewhere there. Okay, so this is the kind of diagram that you are going to expect when you draw your moment diagram. All right, so this whole lot of it, this one here is positive. All right, and when you look at MC is in between 16.875 and the 20.65, just in the middle here. Okay, all right, so this is where our C is. Our C is somewhere here. Okay, so this is about it, and I hope the video was helpful, and if it was, give me a thumbs up, like my video, like my channel, continue subscribing and sharing my videos. Bye bye, and see you in my next screencast.